it's time to talk about time. We have two presentations on time today. One of our speakers not here yet. Late. Maybe didn't synchronize this block correctly. One is this paper is a very seminal paper. You know, like almost every paper in distributed systems cites this paper. Time spots and ordering of events by Leslie Lamport. And the particularly important thing about it is how to think about partial ordering, logical ordering in distributed systems. So then we're also going to talk about real-time synchronization with the NTP protocol. But maybe we'll start talking about this paper.
All right, so just a brief overview so you know the context of when Lamport wrote this paper. He was inspired to write this after reading Maintenance of Duplicated Databases by Paul Johnson and Bob Thomas, because he thought he had a solid visceral understanding of special relativity, which is something he thinks they didn't have. So he thought he could write better about implementing this arbitrary state machine. All you need to know about special relativity, I think, about this talk is, for this paper, is that it teaches that different observers can disagree about which of two events happened first. And there's no invariant total ordering of events in space-time. I'll get more into what total ordering is as we move on. So let's start with the introduction. This is the abstract word for word from the paper. Give you a second to read it. It's a short abstract. Perfect. The words in red is how I'm organizing my presentation, because I think those are the most important critical parts of this paper. These are the key words and phrases. So let's start off with how we humans view time, right? When do we say that something occurred when we use time? We say something happened at 3:15 if it occurs after our watch or clock says 3:15 and before it says 3:16 a.m. or p.m. You can take an airline reservation system, for example. You specify that a request for a reservation is granted before the flight is billed. Kind of pointless if it's made after. So essentially, humans, we really use temporal ordering of systems when we think about time. But machines think different. Quick 101 on distributed systems. The part in bold is important. So just a quick question. If you have a network of computers, right? And if they have negligible transmission delay compared to the time between events in a single process, could you still say it's a distributed system with negligible delay? No, right? All right.
I guess your own computer would be such a system with negligible.
Right. So here's what's different about systems' perception of time, machines' perception of time, and our perception of time. Ultimately, we say the happen before relation is only a partial ordering of events in the system. Bad things happen because people aren't aware of this. Let's move on to partial ordering. This is just a recap. So now we have, say, a specification for a system, right? In order to meet that specification, we're given, as engineers, from some business person, a specification in terms of events observable within the system, and a spec is in terms of physical time. Our system, we know, should not be specified to such a specification. It's impossible to guarantee clock accuracy, right? Big problem. But that's the whole point of this paper. Lamport defines the happen before relation without using physical clocks. This is the happen before relation denoted by this rightward arrow. It has to satisfy these three conditions, the happen before relation. Just give you a second to read the first. Again, the rightward arrow just means happen before. This is the transitivity property, the third property, third condition. So if A happens before B and B happens before C, then you know that A happens before C. And concurrency is when you can't say A happens before B and B can't. You can't also say that B happens before A. Another way to think about this is A happens before B also means A causally affects B. There's a causal effect between the two events, and concurrent events don't have a causal effect with each other.
Just to be clear, it's possible that there's a causal event.
It's possible.
Causal
Yeah,
relation.
it's possible for A to causally affect B. Sorry. All right, so here's a space-time diagram. Now, this is apparently not the traditional way space-time diagrams are shown, because the way Lamport shows it is time goes from bottom to top, and horizontal space represents the horizontal direction represents space. So dots are events, vertical lines are processes, and wavy lines are messages. So let me just ask some questions. You have here the dot, this event P1. What can you say about P1 and R4? So this is P1, that's R4. Can you say P1 happens before R4?
Yes.
Okay. Does everyone agree? All right, that's pretty simple, right? What about P1 and P2? So
Yes.
within the same process, yes? Yeah. How come?
Because they're in the same process. So I think it was like the first rule.
Right. And what about Q1 and P2? These are different events in different processes.
Yes.
Because
There's an event or a request from P1 to or Q1 to P2.
right. What about Q3 to P3?
No.
Does anyone else want to answer why? Yeah.
Well, I mean, you don't have any messages going from from Q3 that come before P3.
Right. The processes Q and P don't know about these events. There's no causal relationship, right? Finally, what about Q3 and P4? So we have Q3 from the previous question, but now it's a different event. We're talking to P4. How come?
Yeah, because Q5 sends a message to P4.
Right, the transitivity property.
Yeah.
Cool. All right, so I think we have a good enough understanding of partial order. Let's go to logical clocks now. Again, you can't think about time the way we think about time. When you think about it like a machine. This is how Lamport talks about logical clocks. Let's start with the top one. So the clock C sub I assigned defined for each process P sub I to be a function which assigns number C sub I of A to any event in that process. So you can think of it like a function where A is an input and what you get is the output of C sub I of A. You can represent the entire system of clocks by this function C. So the distinction between a logical and physical clock is that there's no assumption about the relation of the output of the function C to physical time. So the output's not going to be something like 6:11 a.m. or something, right? Not necessarily. What about correctness? We have no physical time, so the reasonable condition, the strongest one we have is that an event A occurs before another event B. A should have an earlier time than B. Okay, so we can move on to the clock condition. Quick recap from the previous slide. That's actually the clock condition. So note that you can't say this, the converse condition isn't true. So we have at the top that if event A happens before event B, let's just call C of A the timestamp of A. We know that it should be less than the timestamp of event B, but we can't say the opposite. So if we have the timestamp of A and we have the timestamp of B, and the timestamp of A is less than the timestamp of B, we can't say that A happens before B. Does anyone want to fill in the blanks? Because that would imply that any two concurrent events must occur at the same. Oh, great. Here are two conditions that must hold to satisfy this clock condition. This is kind of, we've gone over this. Questions? All right, so now we have another space-time diagram. Now, what's different in this is you have these tick lines, And you can consider the tick lines to be the time coordinate of some coordinate system on space-time. And let's compare it now. It's the same picture as before. And let's compare it to this figure now. You can't say one's better than the other, one's more useful, because there's a lack of physical time concept in this system. We just straightened out the tick lines from the previous image in this one. Okay, so we've had the clock condition. How do we implement this? So let's think of processes as algorithms, and events represent certain actions during their execution. It's important to know that this value of C sub I, what we've been discussing, changes between events. So changing C sub I itself is not an event. We implement IR1 and IR2. These are two implementation rules, essentially to satisfy the clock condition from the previous slide. This we went over IR2. It's just this two-parter. If event A is sending a message, I'm going to Okay, let's talk about total ordering now. Let's just go over the informal method to totally order systems. So the systems of clocks must satisfy the clock condition. We have to order the events by the time at which they occur. In case of a tiebreaker, use any arbitrary total ordering, and then that means precedes that symbol of the processes. This is how Lamport talked about it. So now you have this double right arrow to talk about this total ordering relation. It has to be either I or like 1 or 2, and the total ordering relation is a way of completing the happen before partial ordering to a total ordering. So you need partial ordering before you do total ordering. It's an extension of the partial ordering. It's only the partial ordering which is uniquely determined by the system of events. So per unique partial ordering relationship, you'll have one total ordering relationship. What's the point of all this? Why do we care? This is a classic mutex problem, mutual exclusion. You've got these three conditions. A process which has been granted a resource must release it before it can be granted to another process. We have only one such special resource in our system, and we've got a bunch of processes contending for the possession of this resource to compute whatever they need to compute. Different requests for the resource must be granted in the order in which they're made. And if every process which is granted the resource eventually releases it, then every request is eventually granted. At the end of the system, like whenever it's done running, there shouldn't be any requests done if all these follow, right? We start with assuming that the resource is initially granted to exactly one process. However you want to think about it. There's 5 rules you need to follow to implement this algorithm. I'm going to let you read that, but let's use this diagram that I stole off the internet with credit. You've got these 3 processes, right, which we're talking about, and the circles denote the process, and these are the request queues, these rectangles, and this is essentially saying, this is showing what the first rule says. P1 is our requesting process at this point, and it sends this message adhering to this of the timestamp and the process that's requesting it itself to all of the processes in the system and fills it into request queue. Second rule. Read that. Now what happens? The processes got the request message, and now they send an acknowledgement back to the requesting process, right? Third rule. So P1 releases the resource and removes any T sub n own piece of I request resource message from its request queue and sends the timestamp PI releases resource message to every other process. So this is P1 sending its release messages to other processes in the system. Now we have the request queues of each process empty. Yeah, that's P1 is done using the resource. Kind of is, I think rule 5 is sort of a summary, because yeah, it's just telling you that the following 2 conditions need to be satisfied for P1 to have been granted the resource, which is what we've seen here. So P1 had to receive a message from every other process timestamp later than T sub n. Let's talk about anomalous behavior. So this is a scenario, just recap. The resource scheduling algorithm, the 5 rules we went over, orders requests in accordance with total ordering, signified by the double right arrow. You can still have anomalous behavior. Give you a second to read that. But say you're running like this alpha version, beta version of like Spotify. It's like a terrible version. And it only allows each user access to be able to listen to a song like once. So any song can't be listened to more than one user at a time, by more than one user at a time, right? So you want to listen to Fly Me to the Moon, right? So you're very excited about this, and you add it to your request queue on this terrible version of Spotify, and you call up your friend in Paris, and you tell him, well, I'm very excited to listen to Fly Me to the Moon. And your friend is like, well, I'm excited too now, I want to hear that song too. So they also add it to their request queue, right? But they add it after you've added it. However, on their machine, their request comes up first. It comes up before your request. What happens then? Even you requested earlier, but your request just reached their machine late. We have 2 ways to deal with this. The first choice is we can make the users responsible. Does anyone have any idea what that means? Any guesses how we can deal with this scenario?
Or you call your friend, you open your Spotify app, you read a number, you tell them that number over the phone, and they put that number into their Spotify app.
What's the purpose of the number?
It's the timestamp.
Oh, yeah, okay, yeah. So you basically share your timestamp so that when your friend puts in their request, they know that their timestamp should not be earlier or equal to your timestamp, right? Yeah, that's pretty much what Lamport says too. That's choice 1. Is that a scalable approach? I don't think so either. So we have something called the strong clock condition. Now remember the clock condition from the previous slides. This is a stronger condition, denoted by this hooked right arrow. This is lifted from the paper. So apparently it's possible to construct a system of physical clocks, which, running independently from one another, satisfy the strong clock condition. We have total ordering. But we need physical clocks for this. So I should have specified you need a system of physical clocks. So now we have a need for physical clocks, which is what we're going to talk about. We have to introduce a physical time coordinate T, which we haven't so far because we've just been stressing that we need to talk about ordering of events, not particularly time per se. C sub I of T denotes a reading of the clock, C sub I of physical time T, and that derivative with respect to time represents the rate at which the clock runs at any time coordinate, at any unit of time. So correctness should be that the rate at which the clock runs, the derivative should be roughly equal to 1, right? That means it's going to be running correctly. You have 2 physical clock conditions. The first one essentially just says you need the clock to run individually at approximately the correct rate. It refers to this idea called drift. The second, the clocks must be synchronized for all clocks must be synchronized with each other. Refers to a term called skew. Just important things to keep in mind. So I went over skew and drift in the previous slide, but clocks drift over time. That's what that's your intuitive understanding, which causes skew between the 2 clocks. Accuracy relates to skew relative to a perfectly truthful clock, and I'm sure you understand the difference between accuracy and precision. We have specialized implementation rules for the physical clocks. I won't cover in the same level of detail because I don't understand the math very well. So I have the clock condition for the physical clock condition 2 up there. And the purpose of these specialized implementation rules is to guarantee PC2 is satisfied by the system of physical clocks. The specialized IR1 states that clock reading should change with physical time, and IR2 states that it describes how you synchronize clocks with each other. And this is how it tells you about how to set a process's clock at start of time. So it chooses the max of the current time or the time at which the message is received plus the expected minimum transmission delay. There's a theorem. What it does is that it states IR1 and IR2 specialized versions to establish PC2. Again, I'm going to skip the detail because it's very math intensive. And Lamport also thinks the proof is difficult. So with that, we can conclude. So the concept of happening before is defined in invariant partial ordering. We discussed that 5-rule algorithm. We spoke about this anomalous behavior. Properly synchronized physical clocks can prevent this. Just know that the order in which events occur in a distributed system, multiprocess system, is only a partial ordering. Questions? I'm going to ask this and then. True or false? This was the first question I asked.
False.
Partial.
How about this? Yeah.
Just the other way. Sorry.
Fathered happened before. I guess that's the whole point. Yeah.
All right. So what's the main limitation of logical time in relation to processes within a system? I think this is opinion based.
In the trick question, so if the timestamp of event A is less than the timestamp of event B, so we can say that event A, it's not possible for event A to be affected by event B, right?
Are you saying it's impossible for event A to be affected by event B?
Yeah.
How
So-
can you say that?
If event,
It's true.
Go ahead. I think it's true, what you're saying.
yeah. So it's if event B's timestamp is greater than event A's timestamp, then event B could have been affected by event A, but it's not necessary that event B is affected by event A. But the lowest timestamp, it's not possible that an event with the lower timestamp can be affected by an event with a higher timestamp.
Right.
Saying it the other way.
Yeah, I'm saying it the other way.
Right. I guess what I should have made. I should have made this a true or false question and just made it. You can say there's a partial or it happened before. Then the answer is then you can't say it happened before.
Right.
Yes. Thank you. All right. Let's just discuss what's the main limitation of logical time in relation to processes within a system. I mean, obviously, logical time is a great concept, but something isn't able to be done by it. What do you think that is? Maybe that's a big question. Yeah.
Maybe 2 events occur at the same time. That's
Yeah. I guess what I was trying to think was it can detect failure, but it can distinguish between failure and a slow or paused process, and that is not ideal, right? You want to be able to detect a failed process from a paused or long any process. And final question, why not just use a centralized scheduler to deal with mutex? Why is it preferred to use Lamport solution to this mutex problem?
There's a single point of failure.
Single point of failure, that's one, yeah, that's obviously always a problem with centralized solutions. What else?
Because your whole Frank's not your Spotify thing still doesn't work if the centralized scheduler receives the messages out of order.
Exactly. So we're still not dealing with, I think that was the third or second condition of the mutex problem, right?
So another one, can you do, so we talked about state machine replication, right? State machine replication require that all operations are totally ordered. And so that the replicas have to agree on the operations that are applied and the order in which the operations are applied. Does the, like, which of these techniques could be used for that? All right, the paper. For example, the logical time be used to do state machine replication. Yes.
I guess only if you include like the priority based tie breaking. Or like
So there's this way by which you can extend the partial order into a total order by including some kind of processor ID that's ordered. Is that enough? Yes.
I think the operations need to commute or it can't work.
For it to work, they need to be able to.
Yeah, I think they need to commute because like, the logical time thing allows two different events to have the same logical timestamp. So two different processes could see one is happening before the other. They both have like logical timestamp one.
But it's a logical timestamp is extended into a total order by adding, for example, so lexicographically ordering, first the logical timestamp and then the processor ID or something like that. That fixes any time. So now we got a total order. Question is that enough for state machine replication? Because I said, right, the operations need to be applied in total order. Is it sufficient though?
Still doesn't handle the failure case.
Still doesn't handle a failure case. That's one thing, but I'd say even without failures, it's still a problem.
Can you repeat the question?
So the question is, in state machine replication, all operations must be applied in the same order in each replica. Each replica needs to apply the same operations in the same order in order for the replicas to stay consistent with one another. Can we use this extended logical Lamport timestamp? So Lamport time with is broken by processor ID. Can we use that particular scheme to implement state machine replication?
Maybe you'd have to accumulate a log of all the operations to not actually apply them until you've seen like all of the events less than or equal to n.
You are, I think you're putting your finger on the problem.
Just the diagrams, right? If each process is now like, these are all different state machines, right?
Yeah,
Could that work? If you just apply this.
possibly. I would need to think about that, but let me finish, so Josh says the right thing, so even though we have a total order, it doesn't mean that we have agreement on the set of messages right away, right? So if it could be that one process receives operations A and B, and A is ordered before B, another process receives A and C, but not B. And so applies, and so A is before B and A is before C, but the replicas, so one replica may apply AB, the other replica may apply AC, and now they're inconsistent with one another. Even though the operations are totally ordered, like C goes after B, for example, but the first process hasn't seen C, and the second process hasn't seen B. So there's also, you can't just agree on the total order, you also need to agree on the set of messages, or wait until you have all the messages and then order them or something like that. So there's a little bit more to state machine replication than just total order. And then there's failures as well, right? So these protocols here do not deal with failures.
So Lamport makes a claim in the paper phrased something like any synchronous protocol can be implemented asynchronously using using an extension of this like logical time stamping algorithm. What is he talking about then?
I think it's probably under some weak notion that's probably true. I mean, you can, for example, you cannot measure performance with this notion of logical time, right? Even though, you can just subtract two logical time steps and figure out how many, what the latency is in terms of real time. So I don't think generally
Also, it's technically true what he said, right? Because he never said only total ordering. He said total ordering could use to synchronize. And like maybe it's implied that progressive, like you need this set of messages to be delivered to all different computers.
That's as powerful as saying everything can be implemented using printf.
Yeah, I don't know. I think it's a little bit of an iffy statement. Ollie.
So there's one thing that I'm curious about. So at the end of the day, we have to implement system using this kind of clock. Depending on the implementation, a node may be able to receive requests concurrently, requests that are kind of carrying causality. And then we would probably need some kind of lock on the clock value in order to increment it. And therefore, it's possible that the entity scheduling that reverses the ordering between two messages that have received. So there's some kind of a subjectivity in assigning ordering to events, and I was wondering so we can solve this with physical clocks. If we add enough, physical clocks that are accurate enough, then the scheduler can do its scheduling using that. But is that really what we need here? Can we do it with the weaker abstraction to be objective when viewing the network and the messages that carry clock values with them or causality or anything?
I'm not 100% sure I understand the question. I know that there are certain like real life types of things where people carry about the real time in which operations were invoked state. Like you saw before that when operations overlap in time, it's kind of hard to just because one operation was invoked before another operation doesn't mean that we consider it can still be concurrent. This operation was invoked before operation B, but A didn't end before operation. Only if a first operation ends before the second operation starts do we consider the first operation before the second operation. But then there are real life things where what two people need a kidney transplant, and we somehow want to see which one is first. So we actually very much care about the real time rather than the logical time. There doesn't have to be causal relationship between the two kidney applications. It was done in real time. So in real applications, sometimes you very much care about the real time, although it's also very hard to prove something happened at a particular time. Some kind of secure patent application. Who was the first one to invent it? How do you prove that exactly? Some people do things like publishing an ad in the New York Times just to put a timestamp on something. Yes.
To follow up with the previous discussion, so can we say that if we want to implement a state machine verification, like now we have the total ordering, and then we introduce the idea for like write quorum and read quorum, and to make sure that they overlap, things like we have the larger than to be the majority, then we can safely implement the adjusting of the state.
I don't think so. I mean, maybe if there are no failures, then you can use a protocol like what was proposed here, probably. But in the presence of failures, it's still tricky. In fact, impossible.
All processes need to talk to all processes.
Any case, let's maybe move on. We're gonna talk about new event, Josh.
Yeah, I have one more quick question about the flow of this paper, which is that the whole mutex grabbing algorithm is sort of proposed as like a killer application of logical time and a justification for having a total ordering. But I have a little bit of a suspicion that the total ordering isn't like fully formally necessary for that. And it's just something that programmers sort of want to have for the sake of comfort to be able to reason about. So to make it concrete, do you think that you could implement that same mutex thing using only a partial ordering like vector clocks? Because just looking at the implementation again, I didn't see the point at which it relied on actually having the total ordering.
Two things. My opinion. First, I think the mutex problem was chosen by Lamport because it illustrates in a simple way what he's trying to say. Not so much that like this is the key, like this is the best way to solve it. It just made my point easier, I think, to convey about his algorithm. And two, I think I don't think vector clocks were around when you wrote this paper.
No.
Right. Vector clocks came after logical time. Much later.
True.
Yeah.
But that's what I think. So it was the locus file system.
Vector clock comes to like 1986 something. This is 1970.
78.
So, right, maybe. Oh, yeah, I'm not entirely sure.
I mean, still, look, I don't think that's your question. Your question is
And
just.
the question is like, is a total order actually necessary for that algorithm?
Right. That's great.
It just made it easier to convey, I guess. It was a good example for that.
Following up on that, so if we have vector clocks and then we have a partial order, so can we just not somehow pre-agree to somehow totally order these vector clocks as well, and then we have a similar solution as such? So, I mean, just answering that question. So if we can somehow map this partial order, pre-agree on how we can have a total order, construct a total order, partial order, and then I think if that is possible, we can just use vector clocks to solve
So,
the mutex.
probably, yeah, but I'm not sure that you actually need the total order.
Yeah.
Okay, thank you, Ricky. Let's